So as we start graphing logarithms, we just want to keep in mind that this is the inverse of exponential graphs. So with everything we learned about graphing exponential functions, we're just thinking about the inverse. So let's see how this works. So we're going to have our function 2 to the power of x. So our exponential function, base 2. And then what we'll do is think about the inverse function, so inverse f of x, and that's going to be a logarithm base 2. So the base of the exponent matching up with the base of our logarithm. So first, let's just focus on the exponential. So what we could do is make a table, or as we talked about in making our graphs, we have these kind of key points that we can start with. But yeah, let's start with filling in the table. So 2 to the x, so like this would be 2 to the negative 4 power, which would be a fraction of 1 over, and 2 to the 4th is 16. 2 to the negative 3, which is a 1 over 8. 2 to the negative 2, which is a 1/4. 2 to the negative 1, which is a 1/2. 2 to the 0, which is just 1. And then 2 to the 1, which is 2, 2 squared, 2 cubed. So we have these key points that we can graph here. So start with, we have that 0, 1. It's a key point that we can graph with our exponential functions. And then 1, 2, 2, 4, and 3, 8 we can fit on this page. And then fractions get a little tough, but we can see a half there, maybe even a 1/4. And then from there it just gets really close to the x-axis. So with that, I'm going to draw this as best I can. Alright, that came out nice. Okay, so that's our exponential function. This is our f of x equals 2 to the power of x. And some key points that I want to focus on is this point 0, 1, because that comes through with all of our exponential functions. And then depending on the base, thinking of 1, 2 works out nicely. Actually, so I'm going to just draw that on the other side. And then even this negative 1, 1/2 isn't too bad. But with that, we see some key coordinates. All right, so now let's go to our inverse function. And let's just focus on the table first. So something we talked about with inverse functions is that what we're doing is we're switching our input and output values. So if I needed to make the table from scratch, what I would do is just switch my x and y, where I have input of x, output of 2 to the x. Now what I'm going to have is input of 2 to the x, so we can see our y values from that first table. And then to fill in this column, we're going to grab our x values. So with this first point, we had input of negative 4, output of 1 over 16. Well, now we're going to have input of 1 over 16, output of negative 4. Input of negative 3, output of 1 over 8. Input of 1 over 8, output of negative 3. So we're just flipping the columns of the table. So I can go ahead and fill in the rest, negative 2, negative 1, 0, 1, 2, 3. So let's graph these points. So x equals 1 over 16, which is probably about like right there. That's going to be really close to 0. And what we're having is x equals 1 over 16, y is negative 4. So we're getting this coordinate like right there. And then we're going to have, 1/8, which is probably not going to look all that different with the size of the pen that I'm drawing with here. But 1 over 8, negative 3. So let's do something like that. 1/4, negative 2. 1/2, negative 1. 1, 0. 2, 1. 4, 2. 8, 3. So remember that with our inverse functions, if I imagine this line y over x, I'm not drawing very straight there, we have this reflection over that line. So that's where these coordinates are coming through. But if that's hard to visualize, it's really just flipping the x and y coordinates. So like with exponential functions where we always have the 0, 1, what we're going to see from our logarithmic functions is that we'll always have 1, 0. That's going to be a key point that we can always graph. And then it's going to be this idea of inputting an exponent and getting the output. So like exponent of 1 gives an output of 2, because we're in base 2. So that kind of idea. But if we connect those dots, this is what our logarithmic function will look like. So some things we're going to talk about are domain and range and how those change, and especially our asymptotes. Because with our exponential function, especially when we started graphing, we really relied on knowing that horizontal asymptote, and then when we talked about graph transformations, it affected where it landed. Well, where we had a horizontal asymptote, what we're going to see with our logarithmic function is a vertical asymptote. So it flips because of that reflection that's occurring. But just note that this general shape that's coming through here is overall the same shape as our exponential function. It's just going in an inverted direction. So let's talk about the asymptotes, domain, and range. So we have our original function, 2 to the x. We have our inverse function, logarithm base 2 of x. And let's talk about, actually I'm going to do domain and range first, and then we'll talk about the asymptotes. Or just asymptote, there's only one. Okay, domain and range. So focusing on our exponential function, our domain is all real numbers because we can plug in absolutely any value for x and we'll have an output from our function even as it goes off the page. So domain is all real numbers, so negative infinity to positive infinity. The range for our exponential function, well, if we move along y here, for the blue function, we don't graph anything until we reach y equals 0. And even then, y equals 0 is an asymptote, so we can't have y equals 0, but we're going to be infinitely close to 0, so it's like our function starts at 0.00001, and then we have all values above that for y. So our range is going to start at 0. I'm going to keep this in blue. Start at 0, go off to positive infinity, and with 0 we want to use parentheses because we can't actually have y equals 0, so I don't want to use a square bracket there. Now, writing the domain and range for our inverse function, something we talked about with inverse functions is that if you have the domain and range of the original function, then you just switch the domain and range. So the domain of my inverted function, so the logarithm, would start at 0 and go off to infinity, and then range would be all real numbers. And we can see that that holds true for our graph. In terms of domain for our logarithmic function, I don't have that red function until I reach x equals 0, and even then, that's acting as an asymptote, so we're getting really close to x equals 0, but it never equals, so it's like x is starting at 0.0001, a very, very small number, just a little bit more than 0, and then we have all x values above there. So in our first video talking about logarithms, we talked about how we couldn't plug in negative numbers. That's what we're seeing here. We can't plug in x equals a negative number. We also can't plug in x equals 0. So with that, our values and our domain for logarithm is restricted, and that's something we're going to need to keep thinking about. But then our range is all real numbers because we can see absolutely any output. We can be anywhere on that y-axis and be able to graph our function even as it goes off the page there. All right, the asymptotes. So for our exponential function, our asymptote is y equals 0. So what we're seeing there is a horizontal asymptote. For our logarithm function, we're seeing a vertical asymptote. It says vertical line at x equals 0. So we're seeing this vertical line. Now, as we talk about graphing, we're going to get into graph transformations, and something that was helpful was tracking how that asymptote moved around. And with our exponential function, this moved with vertical shifts. So taking our function plus some number on the outside, it was that number that determined where our asymptote moved to, whether it is up some units or down some units. That created that barrier for our exponential function as an asymptote. Now here, we're inverting everything, so our vertical asymptote will move around, but it won't be with vertical shifts, it's going to be with horizontal shifts. So we're going to see how this moves with horizontal shifts. So as we move x around. So what we want to look for is a number that's being added to or subtracted from x inside of the function, and that'll tell us where our vertical asymptote will land, and that'll help us create this barrier for our logarithm function and how it behaves.